Here we have a concave mirror that follows a section of a curve of a circle, not really a parabola. And they're pretty close as long as we don't go too far from the principal axis. Is it really true that the focal length is equal to the radius of this curve divided by 2? Let's take a look. You got the radius, dotted line. Now we have the incoming light ray as the incident ray, and it's going to reflect such that the angle of incidence equals the angle of reflection. This line is parallel to the principal axis. So this angle here is also equal to this angle here. Well, these angles are all equal then. We have an isosceles triangle. Now keep in mind that this distance here cannot possibly be equal to half of the radius because this is a triangle and it's just not going to work that way. But watch what happens if we make that incident ray get closer to the principal axis. When the angle becomes very small, this distance over here starts to become very close to the focal length. This distance is going to be equal to this distance because it's an isosceles triangle, and therefore we have two line segments that are equal in length, and therefore the focus will be right between the center of the curve and the center of the mirror. So indeed, the focal length will be 1/2 of the radius, which would be this distance right here. As the angle gets smaller, that dotted line is going to lie down right along here. So it's true that as long as we don't have a very far departure from the principal axis, we can say that the focal length is equal to the radius divided by 2. This can actually help us draw some diagrams, because if you know where the center of the curve is, you can just cut that in half and you know where your focus is. It's also helpful to know that any light ray that goes in along the radius comes right back out along the radius too, because it's going in perpendicular to the surface.